Alrighty, we are back, and here comes a biggie. We're going to do some basic calculus. Now, in my classes, we tend to do this basically maybe the first, second, third day of school, whether you've had calculus or not. We learn how to do derivatives. This is about half of calculus, called differential calculus. A lot of big words, a lot of hard-sounding words: calculus, derivative, differential, and all that nonsense. But if you're one of those who's kind of scared just because of the word and you've heard from people that it's hard, my comment is this one here, hogwash. You can do it because I know you know how to do something with graphs. In particular, you know something about how to do slopes. If you understand slopes, and if you can find slopes, you can do derivatives, and you can begin to learn how to do real calculus. After all, this word derivative that we're going to use, that you'll hear a lot of, it's just a fancy name. It sounds hard, but it's nothing more than a certain type of slope. The slope of a tangent line to a curve. Okay? So here we'll just jump right into it. And we'll start off with the simplest curve I can think of, which is a parabola. Okay, use the function y equals x squared. And it's a general sketch of it. And what happens is, the goal is to try to figure out, for a given point on this curve, say here, what's the slope at that point? Okay. Now that too can sound kind of weird because, after all, for a slope, if you just think of the definition of a slope, something you've been doing since Algebra 1. A lot of people, I remember it still, as the rise over the run, which also could mean, a lot of people might write it as delta y over delta x, or the slope equation that you're actually given in math classes is probably written something like y2 minus y1 divided by x2 minus x1. Okay? That's it. So, in other words, you need 2 points on a line in order to calculate the slope of that line. Okay, so what makes a derivative different? Well, because we're talking about curves, really. So, what we can do, in order to find slope, since we do need 2 points, but I'm calling x1 here, and therefore y1 is its y-coordinate. Okay, so for this point, we need a second point if we want to figure out a slope. So what I'll do is I'll arbitrarily choose some other point on the curve, maybe way the heck up here. Now that point has its own x-coordinate. I guess that we could call x2, and its y-coordinate, we could call it y2. Okay, and therefore, if we have those 2 points, then we can draw a line between them, and we can figure out what the slope is of that line, that little dashed line I just drew. Okay, but now, what I'm going to do is I'm just going to jazz it up just a tad with some notation. I'm going to say that this second point is a certain distance away from the first point. I'm going to call that distance delta x. Okay? That's just the space between those 2 points. Now on the y side, if we're using this as our function, y equals x squared, that means y1 is equal to x1 squared, and y2 is equal to x2 squared. Okay, that's just our equation. That's our function that we're using. But there's another way that we can write x2, for example. Okay, so what I'm going to do here, instead of calling it x2, that's the same as x1 plus this little delta x that we're tacking on along the x-axis. Okay? So up here for our y value of that point, x2 squared is the same as x1 plus delta x, that quantity squared. Okay? So it's just notation. It might look kind of weird if you haven't done this before. What I'm going to do is nothing more than apply the slope equation. So the slope between our 2 points that we just drew, okay, we have y2 minus y1. Okay, well, looking back up on our picture, y2, I'm going to use this quantity squared. It's our x value squared. So we have x1 plus delta x squared. y1 is just x1 squared. So we're subtracting that. I'm just plugging into our slope equation. And now in our denominator we have x2 minus x1. Well, x2 we can write as x1 plus delta x, and we subtract from that x1. Okay. This is just the normal slope equation. In fact, over here I'm just going to put down normal, the normal slope. We can simplify this a little bit. Now our denominator is the easiest one. The x1's cancel out, so in our denominator we just have delta x left over. Now on top we've got this quantity squared. x1 squared plus 2x1 delta x plus delta x squared, and then minus x1 squared. The x1 squareds go away. Okay. Cleaning this up a little bit, the remaining 2 terms both have delta x's in there. We can drop out a delta x and simplify this to 2x1 is the first term, and then we're left with a delta x in the second term. So using this notation from our graph, okay, the slope of that dashed line is 2x plus delta x. Okay. We have done nothing. We have done no calculus whatsoever. This is just algebra. This is just our definition, our normal definition for the normal slope. Okay? But clearly, that's not the slope that we're after. I'm going to put in a different color, maybe in green. What we're really after is, by our definition up here, I mentioned that derivative is the slope of tangent line. Now a tangent line is special because it only touches a curve at one point. So the line that we're really after is something like this line. If I could draw that, it's actually touching the graph right there. Okay? I'm going to try that again. Okay, so we want that line, not the dashed line. So the question becomes, how can we get the dashed line closer to the green line, to the line that we want, our tangent line? Well, it really means taking this second point. What if we put it closer to our point of interest? What if we dropped it down to, say, here? Now, if you think of the dashed line for those 2 points, it's not as steep as that first dashed line. In fact, it gets closer to the green line that we want. Okay. Now, how do we do that mathematically? It's all in this delta x right here. If we scooch x2 closer to x1, we get our dashed line closer and closer to the green solid line, to our tangent line. Okay? The way we write this, okay, and this is the transformation that's going to happen, going from the normal slope of our dashed line to the tangent line slope. It's called taking a limit. We want that delta x, we want our second point to get really close to our first point. Okay? And so the closer, remember what we said, the closer that x2 gets to x1, the smaller this delta x is, the closer this dashed line gets to the green line, to our tangent line. Okay? Now, if delta x gets really small, if our second point gets really close to x1, what are we left with? Delta x basically is 0. All we're left with is 2x1. And that is what we call the derivative of this particular function, y equals x squared. So 2x is the slope of this line, is the slope of the tangent line. Now that's really powerful. Okay? So for example, if we had an x value of 2, okay, we can plug that into this derivative equation, this slope equation that we just got. 2 times 2 is 4. So the slope of a tangent line at x equals 2, y equals 4 is 4. If we wanted x equals 10, the slope at that point would be 20. If we wanted an x value of 100 on this curve, the slope would be 200, and so on. Okay, so this is the formal way. This is the formal way of finding a derivative. It's nothing more than taking your normal slope and then doing this limit. So I guess we could say generically, a derivative is a limit as we let that second point get really close to the first point that we're after. Okay, this delta x of your normal slope equation. And we give it fancy words, and you'll see fancy equations in books and stuff, but this is fundamentally what it is. We're not going to make it harder than it needs to be. And we'll do some more. We'll do obviously lots of examples throughout the year of what this means, how to apply it, what it means in physics, and so on. But I just wanted you to get this first fundamental idea in your head. We're doing nothing more than slope equations. And if you can do slopes, you can do some calculus. Okay, more to come. Until next time, thanks a lot.